Guys, what I want to talk to you about today is a topic that I think is actually really, really important, and that is combining first principles simulation and data analysis. Now, the introduction graphic I've got here isn't an accident, and really for me shows the proper workflow of how you combine all these elements. So what we have here is that we have a simple picture of the beam pogo stick model of the race car. We have some correlated data, and ultimately we have the end result. And that really, for me, shows you how you basically bring these elements together. And that sort of really brings me into my introduction. Now, when we come to simulation and data analytics, one of the holy grails of simulation and data analytics is that we have we grab the data, we measure everything up, we hit a magic button, and everything happens straight away. Here's the problem with that. The problem with that is that the real world doesn't quite work like that, because here's the thing. If you don't understand or validate what you have just modeled, you might as well not bother turning up. And indeed, a colleague of mine said to me very, very clearly that simulation without validation is nothing more than speculation. And really, what I want to hammer home in the presentation, today, and I'm sort of glad I'm sort of first cab off the rank here, is that in order to use data analytics and simulation tools properly, you have to understand the first principles behind them. So, to set the scene for this, here's a slide from what I gather, from what I regard as actually probably my most important presentation that I do every year. And I present this to the master's students at Cranfield University in their motorsport engineering course. I also do exactly the same to the master's students in at the German University Horst Trier in their automotive course. And I really want to ram this point home then and now. If we wind the clocks back to 1959, 1960, the Mark III SR-71 Blackbird was designed by 35 guys on slide rules and drawing boards. We went to the moon on computers less powerful than an iPhone. So let's fast forward the clock to now. So now we have all these wonderful computer-aided engineering tools. We've got CAD that will tell you a plethora of information. So let's see where that's got us. Okay, the A380, 3 years late and chronically over budget. And make no mistake, ladies and gentlemen, the fact that the A380 was so late actually torpedoed it being profitable for Airbus. Because make no mistake, it's been said that the COVID pandemic actually killed the A380. Had the A380 actually been on time, Airbus would have made a killing from it. But without a shadow of a doubt, the screening poster child of all this is the F-35. 10 years late and the most expensive target in history. And to really illustrate the parlor situation that we find ourselves in, there was a recent congressional hearing with the U.S. House Armed Services Committee, and Diane Maurer, a senior analyst with the Government Accountability Office, told the U.S. Congress point blank that we've told them that with regards to the United States Air Force's F-35s, they've got three choices. They've either got to cut back the buy, they've either got to reduce flight hours, or they're going to have to cut back on capability. And here's the thing, and the reason that we've got into this mess is that even though we've got a lot of fantastic CAD and computer-aided engineering tools, what we have forgotten is the first principles that drive this, and you need to use both. So let's illustrate this through a couple of case studies. First things first, tire modeling. Now, with regards to tire modeling, the key to any tire modeling, the key to nailing any tire modeling is the traction circle radius versus load characteristics. That is how much force you can get out of the tire as a function of load. If you get that right, everything else will flow downstream from this. Now, a really good approximation from this, and the functional word here is approximation, is that the traction circle radius is the initial coefficient of friction, 1 minus Kb times Fz, all multiplied by Fz. Ka is your initial coefficient of friction. Kb is your normalized coefficient of friction as a function of load, and Fz is the vertical load on the tire. Now, to put some color to this, KA, that's typically about 2 to 2.5 to 3 for a race tire. For a road car tire, that's typically about 1.5 to 2. KB is 5e to the -5. That's a sort of a good rough number to go from. But where things get interesting is that the peak load that the tire will generate its grip is 1 times 2 times KB. Now, here's why it's interesting. That means that any tire can be expressed by the following graphic. That is the peak load at which the tire generated its peak grip, and that peak force is the initial coefficient of friction times the peak load divided by 2. If you can understand that about a tire, you are well on your way to being able to truly understand what the tire is actually doing. Indeed, in the Chassis Sim Bootcamp, I actually go into this at some depth. Unfortunately, because we've only got half an hour, we don't really have the time to dive into that. However, what that means is if you can understand that, what we need to model a tire is we need to have an idea of where our peak load is, and we need to have an idea of the forces the tire needs to generate. So how do we do this? Okay, first things first, what we need to do to answer the question of where the peak tire load is, we need some data, or we need some rough simulation so we can get an idea of where the peak tire load is. Now, the great thing is that can come from log data from the car, or we can put together a pretty rough simulation model to get us into the ballpark. Now, as a rough rule of thumb, I add about 30% for the peak load. So that gives us an idea of the peak load. Is it perfect? No, it isn't. However, at least it's a start point. The second thing that we're going to need is that we're going to need an idea of a rough force balance. So what we need to do is a really good approximation here is a very, very simple deambulant static equilibrium force balance. And that is the total front lateral forces are your front weight distribution times your total mass times IR, which is your inverse corner radius, multiplied by Vx squared. And your rear tire force is 1 minus your front weight distribution times your total mass times IR on Vx squared. Now, the beautiful thing about this is that you can combine this into an Excel sheet. And what you do is that you tune the initial coefficient of friction, and you get an idea. And from your data, you take a look at where your fastest cornering speed is, and the corner radius that corresponds with that, and you tune the initial coefficient of friction to match up the speeds. Now, the beauty about all this, we've just incorporated that into the revised tire force estimation in Chassis Sim version 3.40. So typically what we do here is that we get the end user to generate what we in Chassis Sim call the monster file, which is a single lap or a single data set of your speed, damper positions, lateral longitudinal accelerations, RPM as a function of distance. And then from that, you create a Chassis Sim circuit model, which is your curvature, your bump profile, your altitude road camber. Once you put that in, you basically put in an understeer factor to give you some sort of gauge of what you'd expect in terms of the understeer oversteer characteristics of the vehicle. You press on OK, and it does the calculations for you. But here's the thing: in order to be able to properly interrogate what it's getting back to you, what you need to understand is the driving principle of what makes this work in the first place. And the driving principle of what makes this workplace is filling in the gaps of where you expect to see the peak tire load and where you're generating your peak lateral grip and the forces that correspond to that. Now, in terms of what this produces, here's an example of correlation using this technique. So actual data is colored, the simulated data is black. So what we've got here is that we've got speed, we've got steered angle, we've got throttle, you've got your longitudinal and lateral accelerations, you've got your gear, and you've got your selected gear, and you've got your curvature. Now, this is something that I work through in about 10 to 15 minutes in the Chassis Sim boot camps. And here's why this is so significant, ladies and gentlemen. One of the biggest bugbears, and indeed I would actually say an excuse of why you see people who don't do vehicle dynamic simulation, is they say, okay, we don't have a tyre model, and therefore because we don't have a tyre model, we can't do it. Well, using this technique, this allows you to get into the ballpark really quickly. And indeed, we first started to adopt this in the chassis sim community in about 2015, and it absolutely transformed the way that we did. It absolutely transformed the way we did tyre modelling, and it allowed us to take a tyre model that would usually take us about 2 to 3 weeks to generate it, and we would compress it into about 2 days. But again, where this comes from is some very, very simple first principles and using that appropriately to generate that result, which is why it is absolutely imperative to understand the first principles that's driving your data analytics. The second case study to talk about is range calculation for electric vehicles. Now, unless you've been living under a rock for the last 5 years, particularly in OEM automotive, the only thing people are talking about is electric vehicles. Now, when we come to talking about ranges for electric vehicles, there's a body of opinion that says, right, the only way we're going to do this is through a lot of computer-aided engineering tools, and it's all very, very complicated, and you're going to need to throw a truckload of data at it. Well, I'm about to show you a little technique that really shows this up. Now, the first thing that you're going to need is that you're going to need 2 things in order to do this. Number one, you need to know what your electric engine is going to look like, but you also need to know the power that you need from your application. So whether you're doing this for something like a electrified Toyota Yaris all the way through to a fire-breathing hypercar, it's exactly the same technique. So what you need to do is that you select the appropriate engine. So whether you need an application that only needs a peak power of 60 kilowatts all the way up to 600 kilowatts, you obviously find the motor, the electric motor that translates to that. And you go through and you take a look at, okay, these are the voltage range that the power works. But the real thing that you want to translate it to is the power curve. This will dictate the voltage you're going to need out of the battery pack. Once you've got that, you then take a look at the power you're going to need from the application, and from that you can determine your current. And all that is power is equal to voltage times current. So your current is P on V. Now, in this case, this is an F3 car. It's got a peak power of about 166 kilowatts. So for a typical voltage of about 500 V, that's going to be about 332 amps. Now, once you know that, and once you've got an idea of that, that allows you to start doing your range calculations. Remember, the number of cells that you have in series is going to be dictated by the power of the application. But the number of cells you need in parallel is going to be a direct function of your peak current draw. Now, the way that we can do this is a really simple shortcut. The great thing is that because of the amount of electricity that you've got from the internal combustion era, from your internal combustion data, you've got a lot of really, really good. You've got some really, really good background knowledge in terms of what to do. Now that gives you the ability to approximate both the draw and the current. Yes. So what we've got here is that what we need to figure out is that we need to figure out what our current draw is going to be under full throttle. So what we look at here is the amount of time that you spend on full throttle, which is in this case 52 seconds of the lap. We take a look at our current draw, and that's 4.8 ampere hours. So let's presume you can harvest about 100 kilowatt of energy. So what you've got to do is sum up the amount of time the amount of time under brakes, and so your regen is going to be P on V is going to be 200 amps. So the amount of charge that you can get back is about 0.5 ampere hours. So that's what you get under regen. 4.8 minus 0.5 means that your total discharge is 4.3 ampere hours. So how does that look like when we run this through the Chassis Sim EV toolbox? So what we can see here, the critical thing here is our ampere hour per pack. So what I did was took an F3 model, got an electric powertrain that produced at its peak 166 kilowatts, and as we can see, our ampere hour pack was about 4.18. Now, the great thing about that is we were able to use some very, very simple hand calcs to get us right into the ballpark. And this for me, ladies and gentlemen, really, really nails home how you use both first principles and CAE tools together. You use your first principles to get a rough idea of where the numbers are. You then use your CAE tools to come in and see, right, what are we going to look at? And if you understand both principles, you'll actually see you'll actually see things marry up, and when they don't, that's really your red flag to go, okay, what went bang here? But at least you still have an awareness of the numbers. Okie dokie. Case study 3, some tips and tricks of things to look at. Okay, reverse engineering spring rates. Now, this actually came from a very, very recent job that I did for a colleague of mine based in Japan who runs a CFD company. So he got some data from a formula that has more money than sense and tends to take itself far too seriously. So they gave him some data, but they didn't give him any setup. So what he had to show the end customer is that his CFD tools could actually accurately predict the downforce. So to do that, we needed to figure out what the setup on the car was. And a big part of that is figuring out what the spring rates. Now, here's the thing about spring rates. Spring rates is the change in force over change in spring movement. Now, this car had suspension strain gauges on it. It also had damper displacement. So looking at these slopes here, and this was for the front and this was for the rear, those slopes would allowed us to pull out what the actual vehicle setup was. Now, here's where things get really interesting. If you take a look at that kink in the front, that shows you this car is running a pretty aggressive front bump rubber, and you can see that as the slope takes off. The other thing in here too is you see there's a bit of a spread. That shows you that spring is running a pretty big front bar. Where if we take a look at the rear, the data is a lot more concentrated, which shows you that the rear bar setup over here is actually quite mild. So the great thing about this is we were able to put all this together so that he's now got a platform that he can show the end customer that, hey, you know what, we can now predict your CFD and we can do it quite accurately. The other thing too is what simulation tells you about the car. And this, for me, this particular example really illustrates for me sort of the pet peeve that I've got with modern approaches to simulation. And here's my pet peeve, in the fact that you have an awful lot of people who will go, oh yeah, all we've got to do is we get the information, we put it all in, we hit the magic button, it's going to be perfect every time. That is not the case. And to be quite honest, if that's what you're after, quite frankly, you've come to the wrong place here. And the reason you've come to the wrong place is this underscores a really important thing about what simulation tells you. Now, this particular thing was from a IndyCar customer of mine on a super speedway. So what we've got here is colored is actual, black is simulated. So what we've got here is we've got speed, steered angle, front pitch, which is the average of the front dampers, rear pitch, which is the average of the rear dampers, and we've got lateral G and longitudinal G. So if we take a look at the front dampers, there's a little bit of some minor discrepancies. Mostly it's in the right ballpark. Now, if we take a look at the rear dampers, down the straightaways, it's actually quite nicely matched. But in the middle of the ovals, you'll see there's quite a big discrepancy between the simulated, which is black, and the actual data that is red. Most people take one look at that and throw their toys out of the pram. What this has just shown you is that there is a hole in the arrow map, and this really underscores why you've got to use simulation and data analytics tools as calculators as opposed to magic wands, and I cannot stress that point enough. Okay, the last little tip to talk about is looking at neutral steer and static stability. Now, what neutral steer is that steering angle that we apply if the slip angles are the same front to rear. It's as if you're sort of driving down the road with virtually no force on the car whatsoever. It's a pretty bad analogy, but it gives you the idea. So if we take a look at the slip angles front and rear, that shows us that the neutral steer angle is based on the wheelbase times the yaw rate divided by the vehicle's forward speed. Now, here's where we can pull out a little magic trick, to quote the Joker from The Dark Knight. So what we've got here is AY is equal to VX times R. So the yaw rate can be approximated by AY on VX, which means that delta neutral is WB times AY on VX squared, which is the wheelbase times the inverse of your corner radius. Now, the great thing about that is that it gives, if you calibrate your steer angle at the tire as opposed to the steering wheel, you can quickly overlay these two traces. Anything above that line, everything above the neutral steer line is understeer. Anything below it is oversteer, and it's a really great sanity check, whether you're at a proving ground or a racetrack, where you can see very, very quickly what the car is doing. It's not the last word on vehicle stability, but it's a great thing that you can do instantly to go, hey, there's a problem, I need to look at it. Lastly, before I wrap things up, I want to have a word on correlation. Bottom line, it's the end result. Now, let me walk you through this particular bit of correlation here. So what we've got, again, actual is coloured, simulated is black. And this is actually a V8 supercar at a street course. So what we've got is we've got speed, throttle, front dampers, rear dampers, steered angle, lateral G, longitudinal G, front and rear roll. Let me tell you something, ladies and gentlemen. That correlation sells simulators. I mean, when I reckon that particular correlation has probably sold about 15 copies of Chassis Sim easily. But yeah, here's the point that I want to make. Correlation like that is the end result. It's not your first goal. That correlation came as a result of measuring up the car properly, understanding the tires, understanding the aeros, putting all the elements together. And when those elements got put together, that was the end result. However, if you go for that sort of super correlation straight out of the bat, you will be doomed to disappointment. So to wrap things up, okay, first things first, in order to use simulation and data analysis properly, you must first understand your first principles. That's absolutely key. You then work from hand calculations, and then you do your sim work. Now, in this regard, you're using your simulation and data analytics tools as calculators as opposed to magic wand. And when you do that, ladies and gentlemen, the end results will take care of themselves. Now, at this point, I will conclude the formal part of the presentation, and we'll open it up for Q&A.